Right. First, I'd like to apologize for taking so long for this last addendum, the appendix lecture, because we had the final examination, and after the final examination, naturally we don't have any courses, so we didn't have the time or the opportunity to consider the mistakes that many students have made during the final examination. So I would like to mention some points of the common mistakes from the final examination. This exam gave me a hint about some very significant misunderstandings, but most of the misunderstandings were related to one very important topic, and that significant topic is regarding exponentials or complex exponentials that enter into linear and time invariant systems. They can be discrete time or continuous time, and in the first question, for example, so I will try to emphasize the mistakes from examples. In the first question, there was a system h of z, which many of the students could find accurately. Let's call it, I don't know, 1 plus a z inverse over 1 plus b z inverse. Some system like this. It could be anything, just a function of z, in other words. That's h of z, the z transform of the linear and time invariant system. And in part C of it, the question was as follows: if x of n is equal to 2 over 3 to the power n, then what is the output? As simple as that. That was the question. And without any exceptions, all the students just did it wrong. I mean, all the students who attempted to solve it solved it wrong, because the students mostly proceeded to a misunderstanding, I have to say, of this thing to be equal to 2 over 3 to the power n u of n, for example, which is not. This is not it. And some students even insisted on this way of doing it by saying, okay, then why not this one, 2 over 3 to the power minus k u of 1 minus k, or something like that. The extension to the positive side and the negative side. That is rubbish, okay? Don't even think about it. Although I insisted on the complex exponential version of this thing, I now feel that I couldn't emphasize it enough, that it doesn't need to be only complex, well, I mean only imaginary in the exponent. It could be a real exponent as well. A complex exponential has the real part or the imaginary part. It can even omit the imaginary part, and this is a real exponential. Okay? A real exponential. As simple as that. And what happens when we enter a real exponential or a complex exponential into a system is quite simply as follows: y of n. So first let me write it like this: x of n goes into h, and the output is y of n. Now in the Fourier domain, we expect complex exponentials, in other words, the exponent to be imaginary, e to the j omega sort of thing, because there is only omega that can be handled in this system. Okay. Therefore, we need this one to be e to the j omega, for example, as the input for a specific value of omega, e to the j omega 1, and the output we know to be e to the j omega 1, again, with a t. For this case, of course, it is n. Sorry about that. So the same complex exponential is expected to go out times h of omega at omega is equal to omega 1, this frequency. So it is h of e to the j omega, which is the Fourier transform, evaluated at omega is equal to omega 1. This is from the Fourier. But now that we have a richer class of systems, including the real exponents, we have h of z now. So what I'm telling you, or what you should be able to understand from here, is that if a to the n, where a is not e to the j omega, because if a is equal to e to the j omega 1, for example, a to the n will be e to the j omega 1 times n. But a to the n, where a could be a real or an imaginary or a complex number, when it goes into an h, then the output is again a to the n. But be careful about one point, times h of, now what are we going to write here? The thing that we need to write here is simpler than even the Fourier case. It's not even as complicated as that top figure. It is quite simply h of z, evaluated at z is equal to a. Or you may think of it, this portion, in the same way as well. This is h of z evaluated at z is equal to e to the j omega 1, which is a, because the input is e to the j omega 1 n, that is a to the n. So a to the n goes in, the output is a to the n times h of z, z is equal to a, where a is equal to e to the j omega 1. But for our case, now let's come back to the question. A is equal to 2 over 3 here. So if 2 over 3 goes to the power n, an exponential with a parameter of a is equal to 2 over 3, goes into a linear and time invariant system, discrete time system of course, then the output is quite simply 2 over 3 to the power n times h of z at z is equal to a. So what was h of z? Let's look it up. It was 1 plus a z inverse over 1 plus b z inverse. Alright, no problem. Then this would be 2 over 3 to the power n times 1 plus a z inverse. Z is equal to a, so that is sorry about this confusion. This parameter a is different, so let me put another thing here. Let's make it different. C, let's call it. So this is 1 plus c times, let me first write it like this, z inverse over 1 plus b times z inverse, evaluated at z is equal to a, and that would make 2 over 3 to the power n, 1 plus c over a over 1 plus b over a. Simple. That's it. So the question for this the answer to this first question in the final should be in this form. As simple as that. You don't really need to split this input into u of n multiplying single-sided portions to the left or to the right. It doesn't matter. It's everywhere. It is a to the n. There is no u of n. And the answer should be evaluated in this form. There was, unfortunately, one other question which is somehow similar to that. And where was it? Okay, not that one. Yeah. In number 4, let me remind you about what the question was like. There's a question like this. From this fourth question, I will focus to 2 things. The first is the one similar to this one. So the question was like this: x of n is equal to 7 times cosine pi over 4n plus pi over 10. And there was an h of z. h of z, I will copy from there. It was z plus 0.5 over z minus 0.5 times z minus 0.8. All right. So this is our system, and this thing goes into this h of z. The answer is, what is y of z? You may use anything, including Fourier transforms, z transforms, whatever. It is free. That's what is written over there in this question. But how do we solve it? What's the methodology to solve it? The method is quite simple. Again, there is no u of n. Okay, don't be confused about that. All the students just put u of n here, and then make it a complex exponential sort of thing, times u of n, which has a predetermined, or from the tables you can look up what the z transform of it. So x of n has a z transform if there is a u of n, but as you see, I didn't forget it. I mean, it's deliberately like this, but the question is similar to the top one. So the situation is as follows. You first need to expand this into complex exponentials, because complex exponentials are best to deal with in terms of both z transforms and the Fourier transform, of course. So what is 7 times cosine pi over 4 n plus pi over 10? It is 7 over 2 e to the j, let me open a parenthesis here, pi over 4 n plus pi over 10, okay, and plus 7 over 2 again, e to the minus j, this time, pi over 4 n plus pi over 10. So I'm just representing the same thing in the complex exponentials, that's it. But I know I can find the outputs of the system to these two separate complex exponentials. It's easier to evaluate it that way. When it enters to h of z, and this one also, another component goes in, we will then combine the two. This part will produce the same complex exponential. Okay, that's the trick. Exponential, real or complex, whatever, it goes out the same way. 7 over 2 e to the j pi over 4 n plus pi over 10 times, of course, it is scaled by h of z, evaluated at z is equal to what? You must ask yourselves, what is the value of z here? The value of z here is e to the j pi over 4, right? Because you can also write it like this. This thing could be written as 7 over 2 e to the j pi over 10 times e to the j pi over 4n. You can also write it like this. So these are just some coefficients, but this one is the complex exponential, and that complex exponential is, as you see, equal to a to the n, where a is equal to e to the j pi over 4. E to the j pi over 4 to the power n is e to the j pi over 4n. So z is equal to e to the j pi over 4 is the answer to this output, h of z at z is equal to this, times the original exponential itself, of course, which is here. And to this, the output is 7 over 2 e to the minus j pi over 10, I'm gonna write it separately, times e to the minus j pi over 4n times h of z evaluated at z is equal to a here. What is a? E to the minus j pi over 4. So these are the things that you must substitute. And what does that mean? I mean, how do we do that? It is you may think of it to be simple or complicated, whatever, but you just have to put, for example, this z value, z is equal to a value, into here in terms of z, into here in terms of z, and into here in terms of z, and construct the formula of h of z at this specific value of z is equal to e to the minus j pi over 4. That will give you a complex number. And remember that it's not parametric in terms of z anymore, it's just a number, a complex number. So when the input is 7 over 2 e to the minus j pi over 4 n plus pi over 10, the output is again 7 over 2 e to the minus j pi over 10 times e to the minus j pi over 4 n, which is the same complex exponential, times a number, a complex number, and that complex number is equal to the value of h of z at z is equal to that value. This is not parametric, okay? There is no z, there is no omega, no nothing. This is just a number. It's a number a. Okay. So h of z at z is equal to a is also just nothing but a number. And you're supposed to attack these problems this way. If there is a sinusoid, which is consisting of two complex sinusoids, complex exponentials, or real exponentials, then the way to find the output is h of z at z is equal to a. If it is in continuous time, it's the same. For example, if the input is not a to the n, but if it is a to the t, then the output is, guess what? I didn't ask any question like that, but it could be asked. A to the t going into a continuous time linear and time invariant system this time. The output is again a to the t times, of course it's not the z transform anymore, it's the s transform. All right, at s is equal to what? Now you have to be careful about that. S here s is equal to sigma plus j omega. So you have to convert this into an e to the power sort of thing, like this. If it is, for let me put it this way, if it is e to the 3t, okay, and this is h, then the output is e to the 3t times h of s at s is equal to 3. All right. So what is a in terms of e to the something? That is the logarithm of a will be involved. So this will be a little bit complicated maybe. But nevertheless, you have to be aware that if a to the t goes into the system, a to the t will go out. If e to the 3t goes into the system, e to the 3t will go out. If e to the j 5t goes into the system, the output is e to the j 5t times h of s at s is equal to 5j, right? And that means omega is equal to 5. Or you can also say h of s at s is equal to 5j here, that is equal to h of j omega at omega is equal to 5. That they correspond to the same thing. But this is the case for an imaginary exponent term, that's a complex exponential. This corresponds to a real term. And the mixture could also appear like e to the 3 plus 5j t goes into a system, and the output is e to the 3 plus 5j t times h of s evaluated at s is equal to 3 plus 5j. That's it. I believe that I didn't emphasize on this particular thing throughout the course sufficiently, so I sort of apologize for that, but now that I have the opportunity to explain, I hope some of you guys will have a chance to watch this and get an idea about exponential input, exponential output behavior of linear and time invariant systems. So LTI systems don't touch to the exponential inputs. It touches only in terms of scaling, or including a phase, because that scale could be a complex scale, but it doesn't change it completely. Okay. And another commonly erroneously answered thing was a property for what is x of n as n goes to infinity from the Z transform. Apparently you just couldn't remember, and in the tables I'm not sure whether this one is listed or not, but we did it already. It's in the records, you can find them, and it's in the book as well. This thing from the Z transform is z minus 1 times x of z with a limit z goes to 1. And the proof of this, how come the final value happens to be like this, is it's not very complicated. What you are doing by multiplying with a z minus 1, is happening in the derivative domain. Okay, so it's some sort of a differentiation operator that we are applying, because z times x of z is shifted version of x of z, and then you subtract from that the non-shifted version. So what is the difference between the shifted and the non-shifted ones? That would somehow correspond, if you're thinking of an infinite extent sequence, it is like the derivative or the difference. And then z is equal to 1 would correspond to omega is equal to 0 with a sigma is also equal to 0 case. The proof of this, I really don't want to go into the details, but you can find it. The more awkward or disturbing fact for me is not about remembering or deliberately discovering the proof of this one or not, but you just couldn't remember that. So let me remind you about this one, because in the fourth question again, there was a part which was asking what is the final limit, and in the denominator of x there was a z minus 1 in the denominator. So this z minus 1 is just cancelling that one. And if you may remember, 1 over z minus 1 is u of n in the time domain. So u of n is staying somewhere. By multiplying a 1 over z minus 1, which is u, by a z minus 1, sorry, an extra parenthesis, by multiplying them you just cancel them, and then this happens to be 1, as you see, which somehow gives you a hint that u of n as n goes to infinity will stay to be 1, as you can see from here. So there was a denominator of z minus 1 that should cancel. There were other extra terms, of course, which must be separated into first order systems. A over z minus 0.5 plus b over z minus 0.9, things like that, and you just have to find a and b, and from there, as z goes to 1, what is going to be over there, or even without splitting into a and b, just substituting z is equal to 1 will take care of it, because 1 over z minus 1 is a dangerous term, and that dangerous term goes to infinity as z goes to 1. So you have to cancel that out. Once it is eliminated, the rest is a manageable, evaluatable term at z is equal to 1. Then you could also find it that way. I'm just quickly checking out the other questions, whether I have noticed any other significant problems or not. The others were sort of okay. Specifically, I'm happy with the stability for poles and zeros in the being in the left half plane or inside the unit circle or outside of it, so that the unit circle is included in the region of convergence and things like that. In some students, okay, finally, that's something that I would like to emphasize. Some students were drawing block diagrams with 1 over s. That is nice, by the way. I am not unhappy with it. But this, if this thing is x of t, then what you have here is not x prime of t, okay? 1 over s is not a derivative operator. Be careful about that. It's an integration operator. Again, just think of it like this. To be more precise, it's from minus infinity to t, x of, oops, what is that? X of tau d tau. So 1 over s is not a derivative or differentiation operator. It's not equal to d by dt x of t. If you want to use this one, then you should better use the other way around of drawing blocks like this with an s. Okay, some students just used this and then jumped into d by dt xt. That's a mistake, just a silly mistake sort of thing. I don't think it's a fact that the students just don't know. They are just confused during the examination, I suppose, a few of you guys. So I don't want to insist on this, but I just want to insist that you be careful. 1 over s is an integration. S is the derivative operator. So that's about it. I hope you go through these things for the last time, because once you see signals and systems, the rest of the lectures that you're gonna take in the forthcoming semesters, including the one that has already started, are telecommunications and control systems that are significantly related to signals and systems background. So these concepts, I believe, are quite important as background for the rest of the courses. So for those who pass, I hope that you won't shame me in the other forthcoming control systems and telecommunications courses by not knowing these things. Okay, make sure that you understand these final remarks as well. Okay, so I wish you a successful semester, new semester again, and I would like to I will try to stop at this point.